Welcome to lecture 18. So we are moving towards Navier-Stokes equation now. The Cauchy's equation of motion gives us Newton's second law as a balance of the essentially mass times acceleration on the left-hand side has to be balanced by a body force term, that's typically gravity in our case, and the stress tensor term, where Tij is the stress tensor. And we remarked earlier that this has 13 unknowns, 9 of which are due to the stress tensor, 3 due to the velocity, and then the unknown density. And depending on how you count, you have 6 or 7 equations due to momentum conservation, mass conservation, energy conservation. So we need to reduce the number of unknowns. And the first thing we can do fairly straightforwardly is show that in most cases the stress tensor is symmetric. And this is actually an example in Kundo. You can see how this works. Exercise 436. And that allows us to write Tij is equal to Tji. So if we think back to what is the stress tensor really, let me just write it out. So the diagonal terms here, these ones are our normal stresses, and the off diagonals are our shear stresses. And so if the stress tensor is symmetric, then there's only 3 off diagonal terms really. This means there's in total only 6 unique components. So now we're down to 10 unknowns in the Cauchy equation. That is still not enough. And so what we need, and this is the main part of this section, is we need a constitutive equation, which essentially allows us to relate the stress T to the strain rate tensor S. So before we move on to the constitutive equation here, I wanted to note that the symmetry of the stress tensor doesn't hold in special cases like polarized fluid molecules in an electric field. Now we'll talk about the constitutive equation. For a Newtonian fluid is defined such that the stress and strain rates are linearly related. So we can consider 2 cases. First, in a static fluid, there's only normal stresses and there's no shear, so we only have compression. And if you have only normal stresses, consider like a water bath, then there's no dependence on the direction of the surface that your normal stress is acting on. That means the pressure P is the same in any direction that you consider. So P is the isotropic pressure. And as a result, we can write our stress tensor in the static fluid case as Tij equals minus P times delta Ij, because delta Ij, the Kronecker delta, is the only isotropic second order tensor. And unsurprisingly, that means for isotropic pressure, which has no shear, there's only diagonal components to Tij. So we only have T11, T22, T33. And since it's isotropic, we can change the frame of reference without changing delta ij or Tij. The second case we're going to consider is with motion rather than for a static fluid. And obviously with motion things become a little more complicated. So now we need to account for shear stresses due to viscous friction. And in this case, the concept of an isotropic pressure is kind of lost, because isotropic pressure really is only defined for a static fluid. But there will always be a local intensity of squeezing, so to speak. And so the question is, can we define a dynamic equivalent to P, to the classic static pressure P? And yes, we can. Basically, we'll define P now as the mechanic pressure using the trace of the stress tensor. So consider the trace of T, which is just Tii, i.e. the sum of normal stresses. So now we define the mechanic P bar as minus a third of the sum of the normal stresses. And obviously for a fluid at rest, P bar just reduces to P. We can then partition our stress tensor, Tij, into a isotropic term, P delta Ij, plus a deviatoric stress tensor, tau Ij. So this is called the deviatoric stress tensor, and it essentially refers to all the stresses that are shear. So this is the non-isotropic part, and it's the pure shear part. So the trace tau ii is 0, and this here is the isotropic component. This definition of the stress tensor and the partition into P and tau, as it's written here, is actually slightly different than the formulation in Kundu, and it's the version of G.K. Batchelor's Intro to Fluid Dynamics, and you can look that up in detail in chapter 3.3 of the Batchelor book. So just to iterate this once more, the P bar is slightly different than the standard isotropic pressure, because isotropic pressure is only defined in equilibrium, and a fluid in motion is never in equilibrium. The question is, how do we relate tau, the deviatoric stress tensor, to our strain rate? So tau depends only on our strain rate tensor and not on the velocities or the rotation tensor. Yeah? So tau ij depends on Sij only, which makes sense, right? Sij is the strain rate tensor that describes deformation, and tau ij is the shear stress component of the overall stress component. So in the most general case, relating the 9 components of tau to the 9 components of Sij, you write this as a double contraction of the tensor tau as a function of strain rate S is a 4th order tensor A doubly contracted with our strain rate tensor S. So that's a double contraction, and this thing here is a 4th order tensor. And essentially every element of this 4th order tensor is a constant of proportionality, because we've said that for Newtonian fluids the stress tensor is linearly related to the strain rates. So in index form we have tau ij is aij mn smn, and this really is the simplest way of relating every component of tau to all the components of S.